Standard 10, Unit 1, Lecture 7. Let's move ahead a little more. In previous lecture, we have learned about fundamental theorem of arithmetic, and we have used it to get LCM and HCF of various integers. Here, using that theorem, we are given a question, some special questions, and it is in textbook example number 5. For a natural number n, check whether 4 is to n ends with 0. We have to find out if 4 is to n, value of 4 is to n has any 0 at the end. To answer the question, first of all, we have to factorize 4 is to n. By taking prime factors of 4 is to n, we get that 4 is to n, it means bracket of 4 and out of bracket we can write the power n. Now when we take prime factors of 4, we get 2 square, and if we expand the bracket, if we open the bracket, the power of 2 and that the power is 2 and that power goes outside, so interior power and exterior power multiplies with each other and we get new power 2n. So by taking prime factors of 4 is to n, we get that the prime factor is 2. Okay, and therefore we can say the only prime factor in factorization of 4 is to n is 2, and any number which were to end with 0 is always divisible with 5 and it would contain prime factor 5. But here we can see that 4 raised to n has no factor 5. It doesn't have factor 5. It doesn't have prime factor 5. It has only prime factor, and that is 2. Therefore we can say that there is no natural number n for which 4 raised to n ends with 0. The same way, we have one more question in exercise 1.2, and that is question number 5. In this question 5, we have to check whether 6 raised to n can end with 0 for any natural number n. So we'll solve this question with the same way as we solved example 5. First of all, we will take prime factors of 6 raised to n. So when we take prime factors of 6 raised to n, we get 2 into 3 out of bracket, the power is n, and when we open the bracket, the power n will be written over 2 and over 3. Therefore we can write 2 raised to n, 3 raised to n. It means here in the prime factors of 6 raised to n, we get the not only but two prime factors, and they are 2 and 3. And any number which were to end with 0, it would contain prime factor 5. But here we can see 6 raised to n don't have power 2, power 5. Therefore we can say that 6 raised to n does not end with 0. Okay, here we have two more questions which can be solved with fundamental theorem of arithmetic. Explain 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. These two numbers are composite numbers. To understand this question, first of all we will get the values of the given numbers. For the first number 7 into 11 into 13 plus 13, the value we get is 1014. Now we will factorize this number. When we get prime factors of 1014, we get 2 into 3 into 13 square. Okay, now do you know, if the number were to non-composite number, okay, if the number is prime number, then it will not have factors other than 1 and the number itself. Here we can see that 1014 has factors other than the number itself and 1, and they are 2, 3 and 13. Therefore this value is the composite value. same thing we will do with the next number. Okay, here we get the value of the number is 5045, and in its factors we get 5 and 1009. Okay, so 5045, if it was a prime number, then it would not have factors other than the number itself and 1. But here we can see that 5045 has different factors. Okay, 5045 has factors 5 and 1009. It doesn't have number itself and 1. Therefore, by 1 and 2 we can say that the given numbers are composite. Okay, let's solve the next question, the last question of exercise 1.2. See the question, exercise 1.2. There is a circular path around a sports field, and Sonia takes 18 minutes to drive one round over the path, while Ravi takes 12 minutes for the same. If both of them starts from the same point to drive over the path, what will be the time when they will meet each other at the starting point? To find out answer, we have to find LCM of 18 and 12. So first of all, we'll make the factors of 18 and then factors of 12. So factors of 18 are 2 into 3 square and factors of 12 are 2 square into 3. So LCM, we'll write common factors 2 and 3. In LCM we write every factor, common or non-common. So here we have written factors 2 and 3. And now about their power, now we'll write greater power. In 18, 2 has smaller power 1, and in 12 it has greater power 2. So we'll write 2 over 2. The same thing happens with 3. In 18, 3 has power 2, and in 12, 3 has power 1. So greater power is 2. So we'll write 3 square. And by the value of these factors, the LCM we got is 36. So we can say that both of them meet again at starting point after 36 minutes. So here we finish exercise 1.2, and up to here we have finished the learning Euclid's division lemma and the fundamental theorem of arithmetic.